Good afternoon. I'm Joe Holomuski from the National Research Program, and I'm pleased to announce our speaker today, Dr. Claudia Faunt, who's a supervisory hydrologist with the USGS from San Diego. She's been with the USGS for 27 years. Her first 10 were in Denver, and she moved to San Diego in 1998. In 2013, Claudia became the program chief of the California Water Science Center's Groundwater Framework and Applied Modeling section. Her research focuses on regional groundwater flow systems in the Central Valley of California and in Death Valley of California and Nevada. Claudia speaks to us today on groundwater in California's Central Valley. Claudia?
Thank you.
You're welcome.
This is my pocket. This is kind of a really timely topic with the governor's actions last week. So I'm going to talk about groundwater in the Central Valley of California and some of the conjunctive use that's going on. And Michelle Sneed, John Traum, Randy Hansen, and several others in the Science Center have done a lot of work in the Central Valley over the last decade or so. Michelle particularly on subsidence, and I'll go through some of the work she's done recently on subsidence. So the Central Valley is about 20,000 square miles. Using about 1% of the farmland in the U.S., they produce more than 250 different crops, which supplies about 7% of the agricultural output in dollars, which includes about a quarter of the nation's food, including about half of the fruits, nuts, and vegetables. So in a pretty small area, a huge amount of the food production for the U.S. is done. One other statistic that's rather interesting is about 10 to 20% of the nation's groundwater is pumped from the Central Valley Aquifer System every year, depending on the climate from that year and the changes in agricultural practices throughout the country. So in order to think about the Central Valley and conceptualizing it, this 20,000 square miles is a large sediment-filled structural trough. The average thickness of the sediments is about 2,400 feet, but varies widely throughout the valley. It's generally surrounded by relatively impermeable bedrock, so it's kind of a big basin with a lot of sands and gravels and clays surrounded by the Sierra Nevada more granitic areas, and the only kind of linkage in and out is through the Delta area near San Francisco. One of the big things that's having an effect on the system is development in irrigated agriculture. The major effect is on the volume and distribution of groundwater recharge and discharge. So if you think of the natural system and pre-development, it's a simple system with rain and snowpack on the Sierra Nevadas going down through rivers and into the basin and flowing through rivers and sloughs. But development began in the mid-1800s, and most of the data we have on the system in terms of groundwater and surface water hydrology is after some major hydrologic changes have taken place. Post-development is a much more engineered system with a large canal network and reservoirs controlling the flows in and into the valley proper. So we go from a simple system up here on the top, with irrigated agriculture coming in, affecting the hydrology of the system, changing both the flow patterns below the system and the landscape with all the agriculture and canal systems. And a large part of the area has subsided because of this, and I'll talk more about that later. So in order to understand this system, we've built the Central Valley Hydrologic Model. The USGS Groundwater Resources Program in the early 2000s kind of revisited one of the regional aquifer system and analysis studies that had been done in the past and tried to understand more the hydrology and the storage changes in the groundwater system. So the focus of the study was on groundwater availability and these changes in storage. Originally, this model was 10 layers. We've increased it recently to 13 layers to better understand the shallow parts of the system and to work with the National Water Quality Assessment Program. But we also do a lot of work with the California Department of Water Resources, as well as the Bureau of Reclamation. The Bureau of Reclamation is mainly interested in subsidence and how it affects the infrastructure. And then DWR has done a lot to understand the surface water hydrology and the effects of the engineered canal system and the delivery of water. So the Central Valley Hydrologic Model, CVHM for short, has three main objectives. It has a textural analysis to basically describe the geology of the system, kind of the sediment characteristics and how we estimate the hydraulic properties of the aquifer are based on this kind of textural analysis. The farm process was a systematic approach developed to understand the water budget components of an aquifer system. It's focused on irrigated agriculture, but you can also use it to simulate the natural hydrologic system as well. And we put these together into an integrated hydrologic model. This model is a regional model. It's capable of being accurate at scales relevant to water management decisions, but as you start zooming in on smaller and smaller areas, you need to enhance the details of it. So it looks at the broad picture of the Central Valley as a whole and can be used to understand the effects of this regional system on more local scales. So the textural analysis. This is a 3D model. It's based on about 8,500 drillers' logs. We've recently digitized another 2,000 to put into our database and interpolated the data from those logs to a 1 square mile spatial grid at 50-foot depth intervals. So it's much more detail in the vertical than it does in the horizontal resolution, but it defines kind of the sediment characteristics of the system. So this picture shows kind of a slice through the textural model and kind of looking north. The coarser deposits would be more like the river fans, are shown in oranges and yellows, where the more finer grained deposits are in the cooler colors, the blues and greens. The Corcoran clay, which is a major confining unit, which basically segregates the system in the southern part of the valley into an upper and lower system, is shown by this kind of thin dark blue clay. So this textural model is based on these drillers' logs that were digitized. There's hundreds of thousands of wells in the Central Valley, and we started looking at putting together a set of students to digitize all these logs and quickly figured out we would be doing this the rest of our lives. So that's why we're down to about 8,900 drillers' logs that have been digitized. Originally, we had about 8,500. So you can see kind of the red dots was where we had scanned logs. The black ones were where we digitized, and there's definitely more logs out there and more wells. But the valley in a whole is kind of covered with a lot of wells, and if you take these logs that were digitized into an Access database and try to visualize them, you'll get a distribution that looks like this. And you can see the blues for the finer grained deposits and the yellows and reds for the more coarser deposits. The northern part of the valley as a whole is more finer grained than the southern part of the valley. You get a lot of the gravels and sands coming off the Sierras in the south. And if you zoom in, there's a lot more altering sands and gravels and clays in each of these logs. So on average, the valley is about 35% coarse-grained deposits based on the drillers' logs from all the water wells we looked at. So this shows the distribution of these 8,500 drillers' logs that was put into the original model. This shows the 1 square mile spatial grid, which seems pretty coarse till you look at it on the valley as a whole. This shows like a plan view map of the percentage of coarse-grained deposits in the upper part of the upper 50 feet. And then we're going to kind of drill down through this. Start to see some of the changes in the characteristics of the deposits. And it gets smoother and more generalized with depth. So if you put this in and look at the Central Valley hydrology, the textural model describes what's below the land surface, what's going on in the blues and pinks portions of the system, in the deposits that form the system. But a lot of the changes, like we mentioned earlier, are on above the ground and above the system. And that's what we're going to talk about now in terms of the hydrology. So Central Valley water use before development had a very extensive wetland system. Some of the early explorers talked about when they came over the mountains and hills, the vast expanse of tule marshes and kind of swampy areas, and thought about, wow, this would be a great place to develop agriculture and do a lot of dry land farming in some areas, and then to use some of the wetland areas and route some of the streams. So in 1914, a Water Act came about that addressed the surface water, but had nothing to do with the groundwater system. So until actually the end of last year, this year, groundwater was not really regulated. It's been kind of a local responsibility. Legally, any landowner can pump groundwater as long as it is put to a reasonable and beneficial use, except in adjudicated basins, like most of those occur in the southern part of the valley, like around LA and things like that. Today, water use is much more complicated. There's many municipal and industrial uses, which I'll refer to as urban. There's a large component of agricultural use. We measure the amount of water used to irrigate crops to estimate the water use in the valley, because, as we talked about, the water use is not metered in general. It depends on the crop type, the climate, the different soils, the efficiency of the irrigated agriculture. So there's about 7 million acres of irrigated crops. The vast majority of that is in the southern two-thirds of the valley, the San Joaquin Valley in here, the Tulare Basin down here, with the Sacramento Valley having about 2 of those 7 million irrigated acres. There's also some environmental uses as a term. Look at the flows through the delta and flows that are helping to restore some of the environments of the San Joaquin River restoration. So if you look at this map, there's still about a third of the area that's still native vegetation. So even though the valley looks, as you drive around and look at it, that it's all covered with irrigated agriculture, there's still about a third of the area that's non-irrigated agriculture and is shown in these tanner areas. The browns kind of show kind of the fruit and nut trees, and this is a snapshot from around 2000. So the browns have expanded quite a bit in the last 15 years to about 50% more area than there is now, and I'll talk more about that in a little while longer. The grays are kind of the cotton. The light blue is rice. And this kind of shows the dominant areas for what the land cover is. The reds are the urban areas, so this is the area of Sacramento, Fresno, Bakersfield in the south. So in pre-development time, it's a relatively simple system. There's about 2 million acre-feet of water going in and out of the groundwater system. That's from precipitation coming down and the surface water system leaking into the groundwater system and then discharging back out into the surface water system. So a generally simple system with some interaction between the surface water and groundwater system. With development, I don't expect you to look at all these boxes. The point is, we've made this much more complex. And as a result of all of the groundwater pumping and surface water deliveries to different areas, we have a loss of storage that used to be kind of balanced by Mother Nature on average, and about 12 million acre-feet of water going in and out of that surface water groundwater system. So there's a lot more flow and recycling of the water in the system. So to keep track of that, what we do is develop a hydrologic budget, kind of like a bank account. We estimate the components of the in and out, and every year some amount goes in and some amount goes out. In times of drought, a lot more water tends to go out of the system than goes in. But in hopes, if you have a balanced system, the ins balances the outs overall. To do these estimates, we look at the surface water deliveries, basically the amount of water that both the state and local agencies and federal agencies deliver to different areas. We have different areas that we split the valley up into, and then we calculate the consumptive use of water. We do this with a numerical model that's based on ModFlow. It's called the One Water Hydrologic Model. Randy Hansen in our office in San Diego is the lead author on this. It was originally developed by Wolfgang Schmidt as his PhD dissertation at the University of Arizona. It basically uses a systematic approach for estimating the water components and backs out the amount of water needed based on consumptive use of water by plants, which we can either measure through satellite information or taking crop coefficient and land use maps, get the volume of water that we think is being used, and subtract out the surface water deliveries and the amount of uptake from the groundwater system if the groundwater system is shallow in some areas. This diagram shows the complexity of the system and all the pieces and parts that are put together to understand this bank account and come up with a balance in the different parts of the area, the Central Valley and the Central Valley as a whole. The water use is also driven by climatic variables. It varies geographically and temporally. So the northern part of the valley, up near Red Bluff and north of Sacramento, is much wetter than the southern two-thirds of the valley that is much more arid. There's also variability annually and seasonally. We've been experiencing a lot of this in the last few years with the recent drought. This graph goes through 2003, but shows some of the wetter periods and some of the drier periods. 1976-77 was a historic, very dramatic drought that's shown in here with a lot less surface water coming off of the Sierras as well as a lot less precipitation, if you look at this chart down here. So this shows this kind of a stacked diagram of all the inflows into the valley, and this shows the average precipitation. There was a long, kind of more extended drought in the late 80s and early 90s as well, but was followed by a pretty wet period. And that will come back into effect later when we look at some of the changes in the storage of the system. So in addition to the climate, we've got the land use that we've talked about, and we have three kind of major categories: the urban, native, and crop categories that are split throughout the system. So what has happened through the years is we've developed a conjunctive use of surface water and groundwater. So the surface water components are these inflows from the reservoirs and the diversions from these streams and canals to deliver water to the different farming areas throughout the valley. The other part of this conjunctive use is when there's not enough surface water available, or in areas where surface water isn't available at all, we pump groundwater. The surface water delivery system became pretty mature in the early 1970s. And except during droughts, generally there's a decrease in the total amount of groundwater pumped. But there's a general increase in the proportion of groundwater pumped for urban purposes during this same time. So if you look from this is starting in 1962 going through 2003, it's generally kind of flat and up and down with the climatic period. A decrease in groundwater pumpage from the early 1970s until the mid-80s with the surface water delivery system in place, and then pumping increasing during these drought periods, and then kind of flattening off. There's been some changes in the amount of surface water available, and particularly with the drought areas and drought times, we've had to really change our groundwater pumpage use. So if you look at conjunctive use of surface water and groundwater, basically early in the growing season, in a kind of a typical year like 78, most of the demand, which is shown by this black line, is met by surface water deliveries, which is these green and blue components. Some are routed and some are kind of non-routed deliveries based on how we're simulating the system. And then after you get through about the first part of the season, you start pumping more and more groundwater to meet this demand when there's less surface water available. So in a typical year, it's kind of a cycle with the spring and then the fall with the less pumpage in the spring and more pumpage in the season. However, during the time of drought, like 76 to 77, most of this demand throughout the year is met by groundwater pumpage. So it varies how this surface water and groundwater are used throughout the year and throughout time. So what that results is a change in storage with time. So this graph shows 1962 through 2013, which is the most kind of recent update we've been doing with the model. And basically, you can think of storage as a water level. So basically, in general, the water levels have been declining. They've stayed relatively flat in variable to wet years, but the major declines are in the dry years. These green graphs show the amount of surface water deliveries in the system. So in the really wet years, more water goes into storage, and during the dry years, it declines. The problem is, on average, we are taking out more water than is available, so this graph has a general downward trend and has gotten steeper in the last decade or so, and I'll talk more about the reasons why we think it has gotten steeper. There's been a large number of land use changes. We've switched the types of crops we've had. We used to be traditionally planting field crops like alfalfa and truck crops and tomatoes and things and cotton, where you could just fallow the land if you didn't have water for a year because of a drought or something. We've started planting a lot more permanent crops like vineyards, which are actually relatively efficient with water use, and nut trees like almonds and pistachios. Those trees are a large investment for the farmer. and they're not going to let that large investment go. There's a reason they're planting these trees. They can make a lot more money selling almonds than they can tomatoes, so you can't blame the industry for wanting to make the money. However, they have to keep watering those trees during times of drought. They've also started planting a lot of the fruit and nut trees in areas where there hasn't been surface water available at all, so they're having to pump groundwater all the time. So the land use changes, both an expansion of the land use and the type of crop, have dramatically affected our dependence on groundwater in the system. So kind of to summarize that, the recent drought, land use changes, some restrictions on surface water flows that have been done for different ecological reasons, like in the Delta and for the San Joaquin River restoration, has resulted in large water level declines. And another result of these water level declines that I'm going to talk more about now is land subsidence. So you have these kind of storage changes, which can also be seen by the water level changes. In 2015, we're hitting historic lows at a large number of wells in the valley, particularly the southern part of the valley. And this has resulted in land subsidence. So these kind of yellows and orange areas are where the ground surface has dropped. The red areas are up to like 200 millimeters between 2003 and 2010. So subsidence. In 1960s, the groundwater pumping caused water levels to decline. So part of the rationale for developing that surface water delivery system was to get water into these areas where the ground was subsiding. In some areas, the land has sunk about 28 to 30 feet. So that's a huge decline, and it's not the valley as a whole that's declining. It's more in some areas than other areas, and that has a large effect on the infrastructure, and I'll talk more about that. So after we got the surface water deliveries in place, here's like the low water levels. Water levels rose, except during times of drought. We thought we had this licked. We stopped kind of monitoring subsidence. We kept going on, and then in the drought between like 2006 and 2009, the Bureau of Reclamation came to our office and said, hey, we're having problems with the canals. We're seeing these breaks and cracks, and we looked at some of the GPS data, and it looks like land subsidence has started again. So we started looking into this more. So in some areas, even though the water level declines and these dropping water levels may be a management constraint because it takes a lot more money to pump water and deepen all these wells, land subsidence may actually be a management constraint in some areas because you're breaking the infrastructure, causing damage to buildings and railways and roads. So we started looking more into the subsidence. So what is land subsidence? It's a deep process of aquifer system compaction. It's concentrated in those fine-grained deposits, but if you remember in the textural model, a large part of the valley is composed of fine-grained deposits. And it's these intermixtured sands and clays that make the area very susceptible to land subsidence. So as we pump the water out, the clay particles originally were kind of suspended in random orders, kind of like, I don't know, like plates or pancakes that are kind of sort of floating in your kitchen sink, and at all different angles with like kind of water supporting a lot of them. As you take the water out, these clay particles, which are kind of flat, tend to lay down flat like you stack dinner plates, and they take up a lot less room. So as they take up less room, they compact from this kind of thicker area here to a thinner deposit here, and as that volume decreases, the land subsides. And this is all related to pre-consolidation stress is the term we're using, which is the previous lowest groundwater level. What this also has a kind of effect on, which comes to bear, is the storage capacity is reduced. Once you've compacted these grains, even if you put more water back into the system and recharge it, these grains aren't going to go back to their random orders again. They're going to stay this way. So this is a kind of a permanent loss of storage in the system. So the big reason we care about this is because it damages both the natural resources, the aquifer system itself. It changes the slope of the land, so you're affecting where swampy areas would be and the drainage and where water is going to a surface water system. It also affects the infrastructure. If the valley sank as a whole and the canal stayed kind of flat with its general downward slope, we'd be fine. The problem is it doesn't sink the same everywhere. There's more fine-grained deposits in some areas than others. There's more pumping in one area than another. So different areas are going down at different rates. So a big concrete lined canal tends to buckle or break. That causes the canal to leak. It also reduces the conveyance capacity because the water then has to kind of go fill up a low spot and then go downhill. And it really depends on gravity drainage a lot in the canal. So the canal infrastructure is the one that notices this the most. Talk with the highway transportation groups and the railroad. They experience subsidence as well, but they just kind of adjust the grades and fill and fix things and slowly. And I think in actuality there's probably a large cost with that, but we really don't know what it is because nobody's spent a lot of time trying to figure out how much adjustment's been going on for what reasons. And one of the interesting things to see on this is an oil well drilled near a farmer's field as a test well. They painted the top of the well orange so that the farmers, when they're plowing the field, wouldn't run into it. This was the ground surface in 2010. This is that same well in 2012. So there's about 2 feet sticking out of the ground. So the ground has subsided about 2 feet in 2 years. So that oil well is anchored deep in the system. So it's anchored below where a lot of the subsidence is occurring. That's why the well will pop up and stick out. And that also tends to buckle and break a lot of the wells and metal structure, the metal casings and plastic casings as well. There's been a lot of estimates on the economic impact, but they're all kind of incomplete. There's been some updates to this, but basically it's in the millions of dollars, in hundreds of millions of dollars. So kind of to look at subsidence history, we talked about this. The water levels are pretty much way down kind of low here in the 1960s. As they're still declining, we're getting a lot of compaction, which is shown by this kind of brown area in here. So like there's about 12 inches down in here. A little bit of renewed compaction during the drought, not as much as we had before the water levels were there. And kind of, generally stopped or declined in the 80s and 90s. Fortunately, this well and extensometer are no longer working, so we don't have a continuation of this record. So it's the surface water deliveries that helped stop this. So the engineering helped stop this problem of subsidence. The largest areas of subsidence are down here. This is the California aqueduct trace. So a large part of the original subsidence was along the area where the California aqueduct went. This is the Delta Mendota Canal in through here that we'll talk more about. And here's the Friant-Kern Canal. The location of this well that has this record is kind of near the edge of these two historical subsidence bowls. Today, the major areas of subsidence are shown by these red circles. So we've kind of fixed some of our subsidence areas in this area, but the main centers of subsidence have changed because of these land use practice changes and the availability of surface water. So Michelle Sneed has spent some time recently and published a publication about a year or two ago looking at land subsidence along the Delta Mendota Canal. This is a picture of Joe Poland, who's one of the historical developers of a lot of the techniques we have for looking at land subsidence. And Michelle and National Geographic actually went out last week to recreate this pole. And I'm not going to steal her thunder with that, with the new version of this pole. It'll come out in National Geographic sometime later this year. But what she did do in some areas, because this area generally subsidence has stopped, she went out with kind of a Philadelphia rod and put some measurements together of where some of the more recent high rates of subsidence are. And this is a benchmark with Michelle standing next to it. And the land surface used to be at the top of this sign in 1988. So you can see kind of the rates change in different times too, which is one of the interesting things. So we have a large number of ways to measure subsidence, and it's combining all these where we can get the most accurate estimates because we don't have all the same information everywhere. So we've done spirit leveling, looking at where we actually go out and measure stuff, look at benchmarks, continuous GPS data, which is a side effect of the plate boundary observatory work that's been done, that we try to use that GPS data. And we do a lot of stuff with satellite imagery and INSAR. And then we do some things to actually measure the part of the land subsidence below the ground with some wells and instruments called extensometers. So renewed subsidence became a problem in 2007 to 2009 when the reduced surface waters and the drought hit. So you can see if you look at water levels, which are shown in this blue line, they go up and down. The rate of decline is higher during droughts. And subsidence, the land surface altitude shown by this continuous GPS station, goes down at a higher rate during the times of droughts as well. This picture I showed earlier, but shows the areas of where the subsidence is occurring now. It's kind of where those red circles are. So this is the Bryant-Kern Canal. The edge of it is now being hit. The east side bypass in here, and the edge of the Delta-Mendota Canal. This shows a map of some of that infrastructure as well. The rates, there's a maximum of about 3 inches from 2007 to 10. And between 2003 and 2008, there was about 6 inches in this area. We were actually doing this study on the Delta-Mendota Canal, and the way these images come, we look at these kind of square blocks, and we just kissed the edge of this. And was actually, the Bureau of Rec called and asked us what was going on with their surveys there. They couldn't figure out why they weren't closing and matching, and it actually figured out from looking at some of the imagery and stuff that there's been a lot of landslide centralized in that area. It's not the same everywhere. It's going down at a bigger rate in this area down in here. And these check stations are these numbered structures along the different canal. This shows that some additional work in that area of maximum rate of subsidence. There's about 21 inches between 2008 and 2010. So that's at one spot, if you centered, that's the maximum rate there. But over in this area, you're at about no subsidence. And this shows Michelle in that same picture I showed earlier with about 5 feet between 1988 and 2013. But in different years, that rate changes. And that same type of feature is going on in the area around the Bryant-Kern Canal. So the historic areas with the major subsidence are here. The 2 studies that we've been doing with different types of information are in here and in here where the new subsidence is. So groundwater levels declined about 180 feet since the late 1960s. Some reached historic lows between 2007 and 2010, and since 2013 we've reached even more historic lows of groundwater. This has to do with water level changes and the geologic setting. We need the presence of compactable materials like clays. So if you look at the system, you've got this upper unsaturated unconfined system, which basically means it's not pressurized, it's open more, and water level changes aren't nearly as great. A lot of the pumping is occurring below the Corcoran clay in what's called a confined system. Basically, the water is trapped below this clay. It's recharged up in the mountains at a higher altitude, and this system flows kind of downhill, or at least pressurizes itself downhill, so it's getting trapped under here, and most of the best water and most of the pumping is going below this clay, and this is where a lot of the compaction is occurring. And one of the ways we've been able to figure that out is looking at what's called an extensometer, one that's in the shallow part of the system and one in the deeper part of the system, along with continuous GPS data. So this extensometer anchored at the top of the clay is generally flat. There has been some decline, and more recently there's been even more decline, so we think some of the compaction is now starting to occur above the Corcoran clay, but the land surface is going down at a much higher rate. This is the water level in a shallow well, not changing as much, but the land surface going down. So since groundwater level declines from 2007 to 2010 and since 2012, we're about at historic lows at this well. We're below historic lows at this other well. So this is a shallow well. This is a deeper well, so you can see the more dramatic changes in the water levels in the deeper confined wells. So to kind of summarize the subsidence, we've had about 7,200 square kilometers that have subsided between 20 and 540 millimeters during 2008 to 2010. The data indicates these rates have continued through 2014. A lot of the satellites either quit transmitting or had issues for like 2 years, so we didn't have any data during this most recent drought, the beginning of it. A new satellite just went up in the last few months that we're starting to get new data again. So it's good to have these different ways to measure the subsidence, because you can't rely on one method always being available to use. The subsidence is largely permanent, which reduces the aquifer system capacity. And water levels are continuing to decline because of the heavy pumping. So we need to be able to monitor these water levels and the subsidence to detect the groundwater conditions and look at making decisions. And one of the big things we've kind of learned from this is we thought subsidence wasn't an issue anymore. We stopped monitoring it, and all of a sudden it's back again. So continued monitoring, even when we think things are not an issue, is really important. There was about 20 some odd extensometers put in the 1950s and 60s. We went and revisited them, and were able to re-instrument about 7 of those to start looking at continuing monitoring subsidence. I'm going to talk a little bit more about numerical modeling, but it can be used along with this data and calibrated to that data to look at predictions of where subsidence and water level changes would be based on different land use patterns and different climatic episodes. So what we've done has been updating the Central Valley model. We've done a lot of enhancements to the numerical code and a lot of data updates, and recalibrate the model and have some preliminary results. So the original model went through 2003. We've updated the land use, and with funding from the Bureau of Reclamation, extended the model through 2009, and then some funding available to look at things associated with the drought. We've updated the model through 2013. It's taken a lot of work to update the land use data, the surface water delivery data, and to increase the resolution in the western part of the San Joaquin Valley so we could really look at the subsidence along the Delta-Mendota Canal and figure out how to understand that. So the code changes, ModFlow and both in the application, the Central Valley Hydrologic Model, were updated to include all these more detailed pieces. Those shallow layers were put in more detail. We're separating out the inelastic and elastic parts so we can look at the permanent deformation as well as kind of the ups and downs with seasons. We can actually now simulate the changes in land surface and the changes in slope, and also the compaction of the system to look at the layers actually deforming. And also look at some different solvers and things like that, and adjusting the different land use patterns and the banking areas and how much we know where water is coming and going through time. So if you look at the details of the system, and I'm not going to go through all these details, but if you kind of generally look here, the water is kind of flowing this way. These layers down here are kind of flat. And then we start pumping the water. The actual grid and mesh now deforms and gets thinner where there's been compaction. The land surface altitude and the layer altitudes change, so now that the flows can, in the surface water part of the system, can change to the flow direction, so now the low point is in this area as opposed to over in here for this part of the system. It also affects the uptake of water from ET from groundwater, because it affects the root zone and the capillary fringe quite a bit. So now I'm going to talk a little bit more about some of the data updates. So originally we had 21 areas to kind of look at the details of the system and the surface water delivery, and kind of accounting were done on these kind of 21 larger regions. We first split out some of the details in the delta to look at some of the bypass issues with the peripheral canal. But next we wanted to look at more details along with subsidence in this general area where we had basically one kind of smoothed area for calculating the amount of surface water. We've now split this out into basically the different water districts and how much water they get in those areas. So even though the model has got 1 square mile cells, we're doing the accounting on these larger conglomerated areas, but in more recent times, splitting it out where we have more data. We're constraining the subsidence simulations to basically include leveling surveys, the extensometer data, recent GPS surveys, the continuous GPS data, and also a lot of the satellite interpretation data that Michelle Sneed and her group has been doing. So that's what we've been able to simulate with the actual storage change that you've seen before, and with these surface water deliveries. And we actually simulate the amount of land subsidence, and this is kind of a map showing the distribution of the land subsidence now that used to be largest values over here on the west side is now there's patterns over here on this eastern side where the land use changes have occurred. So one thing we wanted to do with this new code, since we can actually look at the deformation of the surface, was look at the Delta-Mendota Canal and the delivery. So basically the code now links between the surface water and groundwater part of the system with this deformation. So the original base of the canal is this blue line. This is kind of a simulation of the water surface in that canal. And as we simulated from 1961 through 2013, this green line is now the base of that canal. So you can see in this area there's been a large amount of subsidence. So you now have to fill up this valley, this part of this canal, to get it over these humps to deliver the water downstream. So it really affects the freeboard of the system. So what can we do about this situation? We need to kind of focus on keeping groundwater levels above historic low levels if we want to keep from having subsidence incurred. We can enhance groundwater recharge to do that, like artificial recharge through either direct injection or surface infiltration. There's a lot of groundwater banking areas, and I'll show you some data from one in a minute, to where we are putting extra surface water in times where there's wet times or storms, and get that water into the ground. We can look at the natural recharge areas and protect those sources of recharge. We can reduce the amount of groundwater withdrawal. Just like in times of drought, we're talking about reducing our pumping for our natural areas. So we're basically decreasing the groundwater demand, limiting or redistributing the groundwater use, and increasing the supplemental water supply. We need to have long-time monitoring of the water levels and subsidence to detect the groundwater conditions so we can figure out how to make decisions and where's the best place and what change would do the most good for the changes that we can have some control over. We can't really control how the drought's occurring, but we can change how we respond to it. And we can utilize models to assess the impact and to optimize the water use and minimize the impact. So this kind of graph shows some of the recharge from water banking that has been done historically. In the 60s, there wasn't a lot. Started doing a little bit more in the 80s. But in the 90s and even more recently, we've started putting a lot more water in the ground. In these wet years, we've put more than 1 million acre-feet of water into the ground. And this is water that's more available in times of drought. It's making a dent. It's a small dent. I don't think we're going to solve this problem by one solution. I think it's going to take a lot of different things from a lot of different angles to try and get at this issue. And probably part of it may be having to do with land use changes. In the new groundwater legislation, one of the big factors of that legislation was to put the changes into local control. So the local areas need to decide how they want to manage their resource and what will work for them. In some areas, one thing may work. In another area, something else will work. And this lets the local water managers decide how to make those changes. And if they don't make enough to make an impact, that's when the state will step in to affect and figure out how to solve that. So kind of to conclude, in a very small area, we're producing a lot of the country's food. And depending on the year, it's taking somewhere between 10 and 20% of the groundwater in the U.S. to be pumped from this small area, the Central Valley. The recent drought, land use changes, some restrictions on surface water flows have resulted in extensive pumping, large groundwater declines, and as a result, because of the geology of the area, large amount of subsidence. The recent legislation will impact this, and we'll have some changes, and it kind of remains to be seen how that will affect. One of the things we're using is this model, the Central Valley model, along with a lot of smaller scale models, to be a tool to forecast information based on different alternative scenarios. And a lot of these different water managers are approaching different consulting firms or different parts of the USGS to develop tools to try to understand how the different climatic patterns and land use and changes in banking and things will affect things. So with that, I'll finish and answer questions. And this is our web page that summarizes a lot of the work we've done in the Central Valley. Thank you.
So if you have, sorry, my microphone is on. If you have any questions, just raise your hand. We'll find you.
Thank you for your presentation. What can you tell us about the impact of overpumping groundwater on surface water resources?
It depends on where you are. It definitely has an impact, especially where the surface water and groundwater system are very linked, where the groundwater table is up high and there's a lot of surface water groundwater action. As you can expect, if you drop the groundwater levels, there's much more leakage and you have much more of a losing stream from the system. And you also have, when the water levels go up, you have a gaining system. So basically in the southern part of the valley, where it's greater depths to water level, it's pretty much a losing system everywhere already, so it doesn't have a lot of effect, except the subsidence come and kind of changes the patterns and causes kind of swampier areas in some areas and changes the kind of dynamics of the surface water flow, where the flow is coming and going. But it definitely impacts. It's also affected the water quality quite a bit, which I'm not doing a lot of studies on, but there's a lot of studies like CV salts that looks at the agricultural runoff and how that it's changed the water quality in the system. Does that answer what you're getting at?
Claudia, the surface water is measured, so you know how much you're using. The groundwater, on the other hand, is not. And depending on what farmers are doing and land use, how accurate are your groundwater values? Can you compare them with changes in groundwater levels, for example, and how do they balance?
I mean, basically what we do in the model is we estimate that pumpage and use the groundwater levels to calibrate to, as well as the subsidence and the changes in the gauge flow at the different rivers to try to make all that balance. We've also compared in more recent years to satellite data, where we have estimates of the amount of water being lost from satellite imagery type things. So, you know, it's an approximation, but it's what we have right now.
So are you off, what, 5–10%, or what would you say?
I would say in probably getting up, 10%-ish. It depends, but you've got to match those water levels, and you can't change it too huge amounts. And we're starting to do more uncertainty analysis to see how far off we are. From talking to some of the farmers and the metering in different areas, they don't think those meters are even accurate to 10% in some areas. So I'm not sure we're going to even have better numbers once they're metering and compiling that data all together, if everything will be metered as well. Hey, Dave.
Hey. You seem to stress the importance of not drawing water levels below the historical low. If you were to go out and drill a well tomorrow, is there a way to tell what that historical low is, and then you could set that as sort of a monitoring, goal, not to drop it below that?
You could now, because we're in the middle of a drought, so you're probably pretty close to it. But you can actually do core analysis to look at the compaction, and we did some of that when we were doing some work along the Delta-Mendota Canal. We drilled 3 series of boreholes and did compaction tests, where you can actually look to see how consolidated or over-consolidated the sediments are.
So just how deep the compaction goes would be...
Yep, look at the history. What was interesting, and kind of a side note from that, we cored small clays above the Corcoran, as well as the Corcoran clay, and clays below it. And the Corcoran clay itself is actually almost dry in the middle of it because it's so tight. It just, there's not much water leaking in or out of it. It's kind of interesting.
Yes. This is an off-the-wall question, but can you envision a time in the future, maybe 50 years, when desalinization becomes more efficient, that they actually would consider pumping seawater into the aquifers?
I think that's going to start becoming more and more important. I mean, Israel relies heavily on desal. I think it might be, this is kind of my thoughts and not, substantiated a lot, but solar energy was kind of cost prohibitive 20, 30 years ago, and we started, putting money into researching that. Now the solar is kind of everywhere. I think the more and more desal we use, and the way water gets more and more expensive, it'll become more and more economical. They're actually building a desal plant in Carlsbad near my house, and I can start to see that instead of these canals deliver a lot of water to the Central Valley, they also deliver a lot of water to the southern part of California, both LA and San Diego area. And if we can put desal in those areas, use the desal in those areas, and not transport that water and use that for crops, I think that will solve part of the problem. But I think it's going to be an economics issue. I think all of this will be an economics issue.
That's one more along those lines. you know, California produces 205 million barrels of oil per year. And every barrel of oil that we produce 16 barrels of produced water that in some places actually are given to the farmers in Kern County, for example. Now, we can use a lot of that water to replenish groundwater. I mean, we can clean it up a little bit and use it for that purpose. I know in the 90s we actually cleaned produced water to drinking water standards at Class Rita oil field. Have we considered that as an option for replenishing groundwater?
I know Kern County's talked about it quite a bit, and I think it's a great idea. I mean, one of the issues they're grappling with is the chemistry of those waters and how that would affect the aquifer system, and whether you'd be kind of encrusting the system or you know, even just kind of reactions with the different wells and waters there that may cause things that might cause problems. But I think that's a great solution, and especially when everybody's thinking, oh, all this pumping and water and fracking and thing is causing all those issues. Well, maybe it actually could be a solution for part of the problem.
Easy for you. Yeah, you mentioned the compaction tests, and I wonder, were the results you were getting from those consistent with what you see in terms of subsidence as it relates to the groundwater levels? Because obviously the water levels are just telling us about the pressure, and the physical properties of the sediments would determine the response. Does it all kind of fit together?
Yeah, it generally does fit together. It was actually kind of a neat story. And actually you can actually calculate storage properties as well from some of those compaction tests, which were actually done in one of the labs up near here. And it was kind of gratifying because the compaction results from the well actually matched what the model was getting, and we hadn't even planned that, which is kind of a nice thing. But usually you get new results and go, oh, great, this doesn't match at all. So it was nice that that actually matched.
So I have a question. The new groundwater bills that passed last year require a lot more work to decide which basins are going to be monitored. Is the USGS, your office, going to be involved in some of those decisions, to your knowledge, or do you know how?
Well, basically what they've decided in DWR and the State Board have decided is all the high and medium impact basins, which cover, I don't know, it's not that many of the basins, but it's 95% of the use in the valley, are the ones that have to actually come up with a management plan. So all of those areas will have to basically come up with a group to monitor and manage their area and groundwater sustainability management area. I can't SIGMA is what they call the legislation kind of in general. So each of those groups are going to have to come up with ways to figure out what their balance is. And we're talking with both the state and the state board about ways we can help with that process and help the different agencies and maybe develop tools or data we already have, like estimates of recharge and things, to provide information to that system. But we aren't per se part of the regulations or and we're trying to kind of feel our way as to how we're going to fit into all that.
Thanks. Very informative talk.
Thanks.
I have a question about a different realm. I'm used to thinking about these issues in terms of water conservation and resources. What about the energy picture? Is that real significant? I think of, okay, pumping groundwater out, it must take a huge amount of energy, and also if you're using if you're artificially recharging and then draw the water out, is there a big energy cost of that, or is it just kind of negligible compared with the water cost?
I am not an expert on energy at all, but I do know, like, most of the recharging that's being done in the Kern Valley is like spreading. So they just have ground that they're spreading and doing spreading ponds in, so that doesn't take a lot of energy. Pumping it out does take energy. I know the costs of pumping increase dramatically the deeper you go. Drilling a bunch more deep wells costs a lot of money. So I know the energy factor comes into there. How it fits into the picture, I don't know the details of it all. Maybe somebody here knows more about that part of the picture than I do.
I just want to mention, for people who are interested in local groundwater, we have underneath us the San Francisco Cone, which is part of the Santa Clara Basin. And there's been some concern that because Hetch Hetchy water is getting more expensive and the drought, that there's more and more interest in pumping groundwater. So we've been convening stakeholders to make sure that we're managing it sustainably and possibly even looking at recharge with advanced purified water. And if anyone's interested in that process, come see me afterwards and we'll get you plugged in.
Well, let's thank Claudia one more time for a wonderful talk.